Hi, Jihua. How's it going? Okay.
So we're allowed to have a cheat sheet for our midterm, right?
Yep.
Can it be printed out or?
Yep. It can be printed out.
Okay, cool.
Yep. Mhm. Yep, you can use both sides too.
Both sides, yeah,
Yep.
yeah, do that whole word.
Nice.
Condense it.
Yeah. Yeah. Oh, yes, yes, I made the test. Mhm. No, today's topic will not be on the midterm. So the midterm is just going to cover static stuff. Yeah. So I think all the stuff we did last week will also not be on the exam. It's 4 o'clock, so let's go and get started. Good afternoon, everyone. How's everyone doing today? Good, good. Yeah, it's daylight savings, so hopefully everyone got an extra hour of sleep yesterday, or I guess probably in this came an extra hour of work. I guess that's probably more realistic. But it's later in the afternoon, and so it's going to take a little bit of adjusting because it's I'm not used to starting this late, but probably you guys aren't too. All right, and so big announcement this week is that we have our midterm exam, okay? And so that's going to be on Wednesday in class. And so please make sure that you show up in person for that, because there's going to be just like the first exam, there's going to be no accommodations for a virtual exam. So make sure you come in person to take that, okay? As for what you're allowed to bring, remember you're allowed to bring your writing utensil, you're allowed to bring a cheat sheet. And for this exam, because there is going to be some calculations to it with the static analysis, you can bring a calculator as well. And I'm not too picky on the calculator, so it can be graphing calculator, scientific calculator, whatever you feel most comfortable with. So any calculator is fine. And so I'll send an email either later tonight, if I remember, or tomorrow morning, just kind of just confirming all these details. Okay. And a cheat sheet, remember, it's 8.5 by 11. You can write on it front and back. You can type it. You can write it. Whatever works for you. Okay. But just like for the first exam, for your cheat sheet, what I always recommend to people is that you take the time and put it together yourself. And so I've seen people take screenshots from the homework solutions, take screenshots from the lecture notes, and just kind of lay them out in really small print on their cheat sheet. Just to cram as much as they could on it. And what I find happens when people do that is that they kind of spend more time looking at their cheat sheet and trying to look up the specific answer rather than just taking the test itself. And so when you actually take the time and condense the information, put it in a cheat sheet, that itself is a good study mechanism already. And so what you'll find is that if you do that, you'll probably be doing the test and actually not really be looking at your cheat sheet much to begin with. I had a really interesting experience in college, actually. So it was in a Python programming class. They actually let us bring our laptops into the class too. I mean, they brought a Wi-Fi blocker so you couldn't use the internet, but you could actually type code into your computer and then check it for a programming exam. So that's what basically everyone did. But the average on that exam ended up being like a 35% out of 100 because everyone spent so much time typing in their code into their computer and checking the results more than just actually taking the exam itself. And so, I think that was a hard lesson for everyone in the class. And I don't know if the instructor did it on purpose, but he said, yeah, most people just didn't finish the exam because they spent so much time just typing stuff into their laptops that no one ended up taking it. So, I think with the cheat sheet, I think it's kind of the same thing. So, and because I know there's a lot of information to condense. We've covered a lot in this class so far, but really take the time, condense it, and then I think you'll find that it's it's going to help you on the exam a lot. Okay. All right, and so I think that's all my announcements. Oh, actually, one more. So because we're not going to get a chance on Wednesday, I know we talked about the final project maybe a little bit over a week and a half ago, and so only a few people so far have chosen their topics, and so just so that you guys have enough time, just because the final presentation is going to take place. Not the first week after Thanksgiving, but the week after that. And so by the end of this week, so by Sunday, I want everyone to select their topic for the final project. Okay? And so I've already had a few people come forward and claim some. And so exercise biomechanics has already been taken. And I had one student come forward and ask about robotics too. And so I know on the specification, I said only one group can do robotics, but I think I'm gonna see if, because I know that'll be a popular one. I'm gonna see if I can accommodate more than one group for robotics as well. Okay, but I want you to think about it, and I want you to choose a topic by Sunday so that you can start, researching and putting the information together. Okay. Yes. So if you can just send me an email about what your topic is and then who your partners are, I think that would be the easiest. Yeah. Question.
Oh, is the exercise biomechanics one the one where you do the 5 exercises?
Yes. Yeah.
Only one person.
I have a group of 3 doing it. Yeah. That one, maybe we can try to accommodate too. So, if you haven't selected your topic yet, if you can send me maybe a top 3, and then maybe I can try to arrange it. I can try to so that everyone can kind of do what they want. So, Yeah. Okay. And I'll send an email about that too, just because I know not everyone comes to the lectures. Okay. All right. Any questions on anything before we get started for today? Yeah.
I see the final project is 40% of our grade. So do we just not have a final?
No.
Just the final project.
It's just the final project.
Okay. Yep. So all this stuff we're learning right now after the second midterm, we're just going to apply that to the final project instead of being tested on it.
Exactly.
Okay.
Yeah. Right. Yeah. Mm-hmm. It depends. Not the stuff that we're covering after the midterm is probably not going to apply to every final project, but I would like for it to be incorporated in the final project if it's relevant for your topic. Yeah. Mm-hmm. Okay. So there's no more questions. Let's go ahead and get started. Okay. And so where we left off last Wednesday is we were talking about rotational human dynamics. Okay. Right? Because we had just finished talking about our unit of linear dynamics, right? And so, rotational one is the next one. Okay? And this is particularly relevant for human dynamics because, when we talk about human motion, right? A lot of times we talk about a limb that's moving, that's rotating about a particular joint, okay? Okay. And so you can't really have any kind of class on human movement or human biomechanics without talking about rotational dynamics in some degree. Okay. And so, we're going to spend a decent amount of time on this. And so probably, today, obviously Wednesday, we can't have any more lectures, but probably up until Thanksgiving, we'll be talking about this quite a bit. Okay. And so on last Wednesday, we introduced the idea of, what is an angle? How is it measured on the body? And, we talked about angular velocity, angular acceleration. Okay. And so I want to pick it up kind of just right from there. That's it. And so the first thing I want to talk about is some relationships that you can form between linear and angular motion. Okay. Because the two don't exist in a vacuum from each other. Okay, so they are very related. And usually the key that unlocks the relationship is the radius of rotation. Okay. Quick question: for Thanksgiving break, do we have the whole week off? Yes, we have the whole week off for Thanksgiving. Okay. And also, it's not relevant for this class, but on Thursday, Thursday's a holiday as well, and so Thursday the campus is going to be closed. So none of your professors should be lecturing that day. And so if they haven't said anything, let them know, because I actually didn't know until last week either. Okay. All right. And so as an example, the relationship between linear distance or linear displacement and angular, we say angular deformation as an angle, okay? And so the way that you relate them is you just simply multiply by r, okay? And so this is distance. This is angle. And this right here is radius. Okay. All right, so that's distance. We also have a relationship for the velocities. And so we say that linear velocity v is equal to r, the radius, times the angular velocity, omega. Okay. And so this here is angular velocity. And this here is linear velocity. Okay. And then finally, we have a relationship for accelerations. So we have linear acceleration A is equal to R times alpha. Right? Oh, question. So is angle measured in radians or degrees? That's a great question. And so for these formulas, the angles have to be measured in radians. Yeah. Yeah. Thanks for bringing that up. Yeah, because otherwise these formulas will definitely not work. Okay. And that's true for the angular acceleration and the angular velocity as well. And so you would measure those in radians per second and radians per second squared. Okay. All right. And so, on the next page, I'll basically draw an image of this just to make it a bit more clear. But the way that you kind of form these conversions is you just multiply by the radius. Okay. All right. Any questions on this? Okay. All right. And so let's say that we have the simplest rotational case that we can think of. So let's say that we have a rock that's tied at the end of the string, and we're kind of rotating it around. Okay. And so here we have the center. Okay. Here we have a rock. Okay. Okay. And so this rock is kind of rotating around just like that. Okay. All right. And so let's say that over the course of some time t, the rock will displace. Okay. And so it'll rotate to a position right here. Okay. And so this is the rock's position at, let's say, T1, and this is the rock's position at T2. Okay. And the angle that it subtends is called theta. Okay. All right. And so the distance that it travels from here to here, okay, we can call this the arc length. And so I think that's the typical name for this. Okay. Okay. And so the arc length d, or the linear distance, is just equal to the angle that it subtends multiplied by the radius, where the radius is just the distance from the center over to where the mass is. Okay. And then we can find the same thing for the speed. And so the velocity is just going to be the angular velocity multiplied by r, and whatever the acceleration is just alpha times r. Okay. Right. So, but there's a visual that kind of show you what's going on. Okay. But we have to be a little bit careful here for the acceleration. Okay. Because this acceleration right here, this is only the acceleration in the tangential direction. Yes, or the A. Sorry. So the alpha is still angular acceleration, but the A here is tangential. Because whenever you have rotating motion, you have acceleration in two different. You can have acceleration in two different components. Okay, and so you can have one component of acceleration where let's say that we're speeding up the speed of rotation. Okay, and so we can have one aspect of acceleration in this direction, right? Right. And so that would be the tangential acceleration. Okay, and so this component of acceleration would only be active if we're speeding up or slowing down the rate at which we're twirling the rock. Okay. Okay. But when we have angular motion like this, when things are just rotating in a circle, we have another component of acceleration that acts perpendicular to this. Okay. okay? And so this component of acceleration always points towards the center of rotation, okay? And this acceleration is known as the radial acceleration, or some people call it the centripetal acceleration. Okay? Okay. And so even if we're twirling the rock at a constant angular velocity, right? And so let's say that we're not speeding up at all, this radial acceleration is always going to be there, okay? And so the formula for this, let's say it's AR, okay? The formula for the radial acceleration is going to be the linear velocity squared divided by R, okay? Or another expression for it is we can take R times the angular velocity squared, okay? Okay? And so that's the radial acceleration. Okay? Right. And so the reason we always have the radial acceleration is that as we're twirling the rock around, right? The direction of motion is constantly changing, right? And so the kind of the goal of the radial acceleration here is to change the direction of motion as the rock, rotates around the center. Okay. Okay. And to kind of visualize this, let's look at the rock here in these two positions that we have, right? And so if we draw kind of a usual XY coordinate system, okay. Okay. And let's say that the motion of the rock is this way, right here, right? And so if we break this up into the X and Y components, we would have one component that's going vertically down like this, another component going horizontally across like that, okay? But if we compare that motion to, when the rock is down here, right? When the rock is down here, it's going to be, the direction that it's going is always going to be tangent to the arc on which it's traveling on, right? And so if we break this up into components, we would have a direction in the negative Y direction, just like in T1, okay? But the X component, instead of pointing outwards and to the right, now this component is going to the left instead, okay? Because as the rock travels from position 1 to position 2, the direction of its motion is changing, okay? And whenever you have a change in direction of your motion, you have to have some kind of acceleration that caused that change in motion, okay? And so that's the whole point of the radial acceleration, to provide this change of direction that's necessary to sustain circular motion. Okay. All right. Any questions on this? Okay. All right. So let's talk about resistance to angular acceleration. All right. And so what do I mean by this? Okay. And so, if we think back to linear dynamics, right? In linear dynamics, we have basically Newton's second law, right? Okay, so we have basically F is equal to ma. Okay. If I rearrange this formula a little bit, right? And so if I solve for A, what I get is A is equal to F over M. Okay. So nothing really groundbreaking there. But the reason I did this is to highlight this part right here, okay? The M. And so remember, M here stands for mass, okay? And so the more, what this tells us is that the higher the mass of the object we're considering, the harder it is, the harder it's going to be to get it to accelerate. Okay. Right. And so intuitively, we know this, right? And so if we take like a ping pong ball and then we push it, it's going to accelerate really quickly because the ping pong ball has like no mass at all. Well, if we try to apply that same force to, let's say your car, right? So you try to push your car with your hand, you're not really going to be going anywhere because the car is way more massive than the ping pong ball. Okay. And so more mass, remember, more mass is equal to more inertia, which makes it more difficult for you to change its motion. Okay. And so there's an angular equivalent of this. Okay. And so certain objects are going to be harder to rotate than others. Okay. Okay. And so we call that quantity angular inertia, or more specifically, we call it the moment of inertia. Right, and so the moment of inertia depends on two things. Okay? And so we usually give it the symbol I. Okay. And actually, there's a lot of different formulas for moment of inertia, but the simplest one I think is the one that gets the point across the most. Okay. And so if we take the moment of inertia of a point mass, we can get that by multiplying the mass of the object multiplied by r squared. Okay. And the key quantity here is r. Okay, so m we understand, so we know what m represents. Okay, so this r right here is the distance from the axis of rotation. Okay. And so what this says is that the farther away a mass is from the center of rotation, the more difficult it's going to be to rotate. Okay. Right, so this is different, right? And so, for linear motion, the only thing that it depends on is just the mass of the object, right? But for angular motion, we have to take into account both the mass of the object and also its radius of rotation. Okay. And so, if we can bring this back to human motion for a second, right? And so what this tells us is that the distribution of mass with respect to an axis of rotation can dramatically influence, how the ease of the body motion. Okay? And on the next page, we'll go over an example of how the body actually takes advantage of this to increase the efficiency of the motion. All right. Any questions on this? Okay. All right. So let's do an example real quick. Okay. And so let's consider let's consider just a normal person sprinting from one place to the other. Okay. Okay. And so if we take kind of a side view of someone sprinting, right? And so we take kind of a snapshot, they might look like this. Okay. So they might maybe have, 1 foot on the ground and their other leg, it's probably going to be bent up like this. Okay. I want to focus on this leg right here. Okay. All right. And so as this person's sprinting, right? And so the idea of sprinting is to get from point A to point B as quickly as possible, right? And so in order to do that, you have to swing your legs as quickly as possible, right? Because each step that you take gets you closer and closer to your goal. Okay? And so throughout the sprinting motion, you know, we can approximate each leg as approximately like a pendulum, right? And so, you know, this leg, what it's going to do in the next stage is, in order for this person to move forward, this leg is going to need to rotate this way, right? And so if you think about when you're sprinting, right? And so when you're sprinting, you have one leg off the ground. The next thing you're going to do is you're going to bring that leg forward, right? And so one way we can quantify that motion is a rotation about the hip joint. Right? Right? And so in order to maximize the speed, right? And so in order to maximize your sprinting, you know, we want this leg to swing forward with the least amount of resistance as possible. Okay. And so, you know, one thing that the body kind of instinctually does to help this rotation is that you tuck your heel in towards your butt, right? And so you don't, and so you never see anyone sprinting with their full leg extended, right? And so when they after one leg takes off, right, the other leg bends back as far as it can, okay? And the reason for this is, you know, when you bend your leg back like this, you bring more of the mass, more of the distributed mass of the leg closer to the axis of rotation, which is the hip. Okay. Okay. Right. And so the advantage that this gives us is that, you know, as we bring our legs closer to the hip, right? And so if we remember our definition for moment of inertia, right? Remember, moment of inertia is mr squared approximately. Okay. Right. And so when we bring our leg closer to the hip, what we're doing is we're taking this r squared term and reducing it. Okay. Okay. And so by reducing that r squared term, we're going to lower, we're of course going to lower the moment of inertia. Okay. And by lowering the moment of inertia, it's going to make our leg swing a lot more easy. Okay. Right. And so this is something that the body kind of naturally does on its own. But you can also utilize this, this information to optimize sport performance too, right? And so, you know, I never did track in high school, and you know, I didn't really fully appreciate it until, you know, kind of recently when I was preparing for this class, right? And so, you know, when you're running competitively, when you're trying to achieve the best time, you need to really optimize a lot of aspects, a lot of the mechanics if you're running like this, right? And so, a lot of when sprinters train, of course they have to do strength training. That's really important for them. But another thing is for them to optimize, the motion of their sprinting, right? We may not think about it because, when we sprint from one place to the other, we don't really think about how we're doing it. But when sprinters are training, they really, train on this. And so when they take off from the, when their leg takes off, they try to bring their leg close to their body as soon as possible so that they can rotate a lot faster. And it may not seem like a big optimization, but lots of little things like this really makes a big difference in their performance, even if it's just by a few tenths of a second. But for sprinting, that's a huge thing. Okay. And so there's a lot of things like this that the body can take advantage of in order to optimize its motion. And all of it just takes an understanding of what the moment of inertia is. Okay. All right. Any questions on this? Okay. All right. And so that's a moment of inertia. And so now let's talk about angular momentum. All right. And so, we're going to build off basically what we understand about linear momentum and talk about it here, okay? All right. And so just like linear momentum, we use angular momentum as, the quantity of motion that an object has as it rotates, okay? Okay. And the key here is that it's a quantity of motion. Okay. All right. And so its definition is very similar to the linear momentum definition. Okay. And so we're going to take a product of the quantity of inertia, okay, multiplied by the quantity of velocity. Okay. And so for linear momentum, remember that was the product of mass times velocity, right? So that's how we compute linear momentum. But for angular momentum, we're going to take the product of moment of inertia and the angular velocity, okay? And the symbol that we usually give for angular momentum is h. Okay, so this h here is angular momentum. This I here is moment of inertia. Okay. And this W here, of course, is angular velocity. Okay. All right. And all of the complications that come with moment of inertia that we just talked about, become associated here as well. Okay. And so depending how the mass is distributed in an object, that of course is going to change the moment of inertia, and that of course is going to affect the angular momentum as well. Okay. So just kind of keep that in mind. All right. And so one particular aspect of angular momentum that we have to talk about for human motion is the this fact that angular momentum can have multiple contributions. Okay. Okay. And so the human body is known as what's known as a multi-segmented object, okay? Because we're comprised of multiple segments. Okay. And so in these situations, there can be multiple contributions to the angular momentum. Okay. Right. And so the first one is known as the local term. And so the local term, what it does is it characterizes the rotation of the body about its own center of gravity. Okay. Okay. And so COG there stands for center of gravity. Okay. Okay. And so the other component is known as the remote term. Okay. And so what this does is it characterizes the rotation of the body itself around, the total moment, the total center of gravity. Okay. Okay. And I'm going to draw a picture of this on the next page just because it's a little bit hard to visualize just from these definitions. Okay. All right. So before I do that, are there any questions on this? Okay. All right. And so let me go ahead and draw a picture just to kind of make this a little bit easier to visualize. Okay. And so let's kind of take the opposite situation from the sprinting. And let's say that we're considering the motion of someone kicking a soccer ball. So let's say that we have a person here. So let's say that he has one foot planted and the other foot is winding back to kick a soccer ball. Okay. All right. And so let's focus on just the motion of the lower leg. Okay. And so as this leg kind of comes down towards the ground to kick the soccer ball, right? This lower leg itself is going to rotate. Okay. And so if we say this is the center of gravity of the leg, okay. Okay. And so in order to perform this motion, that leg itself, if we consider the the center of gravity of the leg to be right there, right? That leg is going to be rotating around its own center of gravity, right? And so, basically the leg is going to go from, kind of slightly horizontal like this until eventually it contacts the ball. And when it contacts the ball, it's going to be roughly, we're going to assume it's roughly vertical. And so if we assume the ball is like, maybe the ball is right here, right? Okay. And so when the leg strikes the ball, it itself is going to rotate. Okay. But another component of the rotation has to do with the fact that, this person's own center of gravity is probably around here. Okay. And then as this leg is brought forward, it's also going to be rotating around this center of gravity as well. Okay. And so this motion, would be something like this. Okay. And so if I draw kind of a vector here, okay, so we'll call that vector R. And so that vector R is going to connect the center of gravity of the person's total body and the center of gravity of the lower leg itself, okay? Then what we can say is that the total angular momentum of the leg is a combination of these two motions together. Okay, so what we can say is that H total is equal to, okay? And so first we have ISWS, okay? And so this term right here is the local term, right? And so that's the rotation of the leg itself around its own center of gravity, okay? Okay, so this is going to be the local term. And then to this, we're going to add m r squared times omega g. Okay? And this term right here, this is our remote term. Okay. And so the total angular momentum is the sum of them both. Okay. Yep. Yep. And so the local term, you know, this is right here, you know, that very much may very well be like an mr squared. But because the leg is a distributed mass, and so the mass of the leg is distributed around the center of mass right here, then normally we have another equation that we can compute is with.
Can we consider it a rod?
Yes, exactly. Yeah. And so one approximation is that you consider it as a rod, and I think I have the formula for it later. I think it's like 112.
Technically, it's not uniform length, right? Because the cap could be bigger at the top and smaller at the bottom.
Exactly. Exactly. Yeah. 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 And so if you assume it to be a uniform rod, then you have 1/12 ml squared. But yeah, because the leg itself is not a uniform rod, you'd have to adjust for that in some way. But I think a uniform rod is a pretty decent approximation. Mm-hmm. And so this is right here is the local moment of inertia. Okay. Which depends on geometry. But for most of the human body, you know, for most of the segments that we're interested in, a lot of times it's our arms and our legs. You know, most of the times we just assume this to be a uniform rod, which we'll cover later. Okay. All right. Okay. And so we have both of these contributions to the angular momentum. Okay. All right. Any questions on this? Okay. All right. So let's talk about conservation of angular momentum. I feel like conservation of angular momentum is like the one thing. Oh, sorry. Was there a question on the last one? Oh yeah, yeah, yeah. We'll touch base on this after the lecture. Yeah. Mm-hmm. All right. So I feel like conservation of angular momentum is I think the one thing that most people remember from their basic physics class, but they don't actually remember what the name of it is. But I think once I start going over some examples, I think you know, hopefully it'll jog some of your memory. Okay? All right. And so, you know, angular momentum is one of those other conserved quantities. Okay. Right. And so, you know, we have a lot of conservation quantities in applied physics. And so we have conservation of energy, conservation of linear momentum, conservation of angular momentum, conservation of mass. And so this is just another one of those. Okay. And so what the conservation of angular momentum states is that in the absence of external torques, okay, in the absence of external torques, angular momentum is conserved. Okay. Right? And so unless you're applying an external torque on an object that's rotating, its angular momentum is going to be conserved. Okay? One key point that I want to make here is gravity. Okay, and so gravity, we always assume that gravity acts through the center of mass of an object. Okay. Okay. And a lot of times, we consider the center of mass, excuse me. A lot of times we consider the center of mass to be the axis on which we're rotating around, okay? But since gravity acts right through the center, right? It acts basically exactly the same as our joint forces, right? And so if we look at our joint forces from our static analysis, because the joint forces act right at the joint where we're rotating, it doesn't contribute to any kind of, torque, okay? And so gravity alone usually doesn't provide any torque to a body. Okay? Right. And so the conservation of angular momentum basically says that the angular momentum in one phase is exactly the same as the angular momentum in a different phase, okay? Assuming that we don't have any, external forces or external torques, okay? And so what this tells us is that the product of moment of inertia times angular velocity in state one has to be equal to the product of moment of inertia and angular acceleration in state two, okay? All right. And so let's start with, I think, kind of the most famous example is an ice skater that's kind of twirling on its own feet, during an ice skating dance. Okay. Okay. And so let's say that let's draw an ice skater. Okay. Okay. There's my terrible deformed ice skater. Let me fix his leg a little bit. Okay. Better. All right, so let's say that we have an ice skater that starts out like this, and he has his arms out to the side, and he's rotating, okay? And so he's spinning on the ice. Right? I don't know any recent famous ice skaters, so we'll say this is Michelle Kwan, because that's the only one that I knew. Asian American hero for young Asian American growing up, right? Okay, and so let's say that Michelle Kwan is rotating like this, okay? So she's spinning on the ice, and then in the next phase, what she's going to do is she's going to bring her arms close to her body. Okay. So let's say that she brings her arms closer in, okay? She's still rotating, okay? So she didn't stop her rotation, okay? But because she brought her arms closer to the body, what we can say is that the moment of inertia in state two right here is lower than her moment of inertia in state one, right? Because remember, when you bring the mass closer to your axis of rotation, that's going to lower your angular or your moment of inertia, okay? And so, since I2 here is less than I1, in order for the angular momentum to be conserved, what has to happen is that omega 2 has to be greater than omega 1, right? And so you can see this kind of very, very, very easily when you watch any kind of figure ice skate, okay? And so, a lot of times when they go into a spin, they'll have their arms far away from their body. But then when they bring their arms closer, they suddenly just start spinning faster, right? And it's not a visual trick at all. They actually are spinning faster. And it's because their angular, their moment of inertia has gotten smaller, but their angular momentum is being conserved this whole time, okay? You can try this at home too. And so you don't have to know how to ice skate. And so if you have one of those office chairs that spin, right, you can sit in the chair and you can extend your arms and your legs and have your buddy kind of spin you around, okay? And then once you've achieved a good speed, bring them close to your body and you'll find yourself rotating a lot faster, okay? I would recommend you do this before you eat dinner, just so that you don't throw up all over the carpet, which is what I've done in college, actually, which is not a memory that I want to revisit, but you know, it's a funny story that me and my friends we remember. But that's one thing you can do to try it. Okay. All right, any questions on this? Oh yeah, I think a lot of us have tried it at some point. Did I drink too much? No, I actually did not drink at all. Would have been worse if I drank anything. Okay, let's do one more example. Okay, so I think that's the classical one. I think that's the one that everyone, I think every physics teacher on the planet shares when they teach about angular momentum. Okay, but let's talk about maybe one that's not talked about, right? And so let's talk about volleyball. Okay, and so in volleyball, you know, one thing that happens a lot is that a player will go up and hit the ball at the net, right? And so we call that a spike. Okay? And so, you know, let's say that a player, it's a big head. Okay, so let's say a player will jump up, okay? And let's say the ball is right here. Okay. And then to spike the ball, right? So what the idea of the spike is you want to hit the ball down towards the ground, okay? And so in order to do that, he's going to bring his arm around, okay? And basically rotate his arm around the shoulder, right? Okay. And so it's basically an angular motion, right? And I think it's angular motion in kind of its purest form, where you have a limb that's fully extended and it's just purely rotating around the joint, right? And so the arm here is rotating around the shoulder joint. All right. And so that's that's already pretty clear. Okay? But you know, when the player jumps off the ground to perform the spike, you know, usually when you jump off the ground, you're not really rotating at all, right? And so when you jump off the ground, you usually just jump straight up, you come straight down, okay? And so your angular momentum, when you jump up, is actually 0, right? Okay. And so when you jump up, you jump down, you're not rotating at all, unless you're trying to do a back flip or a front flip. You know, maybe you had something to drink, I don't know, but usually you're not trying to, the goal is not to rotate when you go up, okay? All right, but, you know, when you swing your arm to, to spike the volleyball, right? This is going to create some angular momentum, right? Right? Because you have your arm, and so your arm has some mass, right? And so your arm has some mass that's distributed away from your center of mass, right? And just by the fact that you're rotating it with some speed means that there's going to be some angular momentum associated with that motion, okay? Okay. But how can that be, right? So how can we jump up and have no angular momentum, and then suddenly do a motion that does have some angular momentum, right? And so it seems like these two ideas are contradictory to each other. Okay. It's not, and so it's an internal torque, and so that's the key here. Yeah. Mm-hmm. Yeah. And so for those of you on Zoom, so the question that was asked in the class is, does it count, the fact that you're using your shoulder to bring your arm around, does that count as an external torque so that we violate conservation of angular momentum? And so, my argument is to say that it's not. Okay? And so because the muscle force is an internal force within your body, it doesn't count as an external force. Okay. And so, as you swing your arm, we're still saying that no external torque is being acted on your body. Okay? And so how can that be, right? So how can we have zero angular momentum, but we can swing our arm? Okay? One thing that, that your body does to counteract this is that it creates a counter rotation at a different part of your body, right? And so what if you kind of watch some very slow motion video of a player spiking a volleyball, you'll obviously see their arm, rotate forward to hit the ball, right? But at the same time, what you'll notice is that their legs are going to rotate back, right? And so, usually it's at the knees. And so I kind of made this guy kind of a hobbit, okay? And so what you'll see is that as the arm comes to rotate forward, the legs start to rotate back, okay? And so what you can see here is that as the legs rotate back, they create an angular velocity, we'll call this omega 2, in the opposite direction, right? Okay. And so if we sum these up, right, and so we say that the total angular momentum of the body is equal to the moment of inertia of the arm times the omega of the arm, which we'll call omega 1, okay, plus I of the legs times omega of the legs, okay? Where in order for this to work, omega 1 and omega 2 have to have the opposite sign. Remember, they're rotating in opposite directions, right? I'm sorry, yes, yeah, they're both rotating clockwise. Yes. Yes, so they're both rotating clockwise. But basically the moment of inertia of the legs are used to counteract the motion of the arms. Okay, but why? It should be the opposite way. Actually, yeah. So the legs actually kick forward. Yeah, the legs kick forward. I'm sorry. I wrote it indirectly in my notes. Yeah. And so after you spike the ball, your legs actually come and rotate forward. I'm sorry about that. I had written down wrong in my notes. Yeah. And so as you kind of bring your arms forward, then your legs have to also kind of kick forward too, so that they rotate in the opposite direction. Okay. I have to correct that in my notes. All right. Yep. And so if the legs are rotating forward, you can see that they're going in opposite directions. Okay. And so if they're going opposite directions, then we can maintain the total angular momentum of the body to be 0. Okay.
So Professor, if that didn't happen, basically every time you tried to do a spike, depending on how hard you did it, you just end up doing it wrong.
You could, yep. It would be really hard to do just because because the limbs in your body and the joints would just kind of naturally just do that anyway. But if you tensed your muscles enough so that you kind of prevent that rotation, and so let's say you tense your abs, you tense your back so that you don't actually you don't bend forward or anything like that, then you would just keep rotating like that. Yeah. It's very hard to do in practice, but in theory you could do it. Yeah. Mm-hmm. All right. Any questions on this? Okay. All right. Another instance where not the human body, but a cat's body takes advantage of this is when a cat is falling, right? And so if you've ever dropped a cat or if you've seen a cat fall from a high place, you notice that the cat always lands on their feet. Okay. And so cats also take advantage of the conservation of angular momentum to kind of rotate themselves into the proper place. Okay. But I'll leave that as a homework problem for you to explore. And so, I'm gonna link you a YouTube video that I really like that does a really good job explaining this. And then, you can take a look and kind of summarize it. So I don't want to spoil anything, and so I think we should watch the video and see. All right. All right, so let's talk about angular impulse. Okay? So remember when we were talking about linear momentum, the way that you change the momentum of an object is to apply an impulse, right? And so you apply a force over a certain amount of time. Okay? For angular momentum, we have the same quantity. Okay? Okay. Right, and so if we have a product of torque times T, okay, this is going to be equal to the difference in angular momentum in two different states, right? And so this can be equal to H2 minus H1, okay, which of course is equal to I omega 2 minus I omega 1. Okay. And so another way that we can express this angular impulse theory here, to kind of, to take the limit as t approaches 0, okay, is we can say that the torque, or the sum of the torques around an object, is equal to the moment of inertia multiplied by the angular acceleration. Okay, so this formula right here is basically Newton's second law, but for angular motion. Okay. All right. And so, probably not today, because we are running a little bit short on time, but probably on next Monday, we'll actually start to use this in some angular dynamics problems. Okay? But, just want to make sure that, that we cover this formula just so it doesn't come as a surprise once we get there. All right, any questions on this? Okay. All right. And so let's talk briefly about the parallel axis theorem. And so if you recall from probably your previous classes, the parallel axis theorem has to do with how do you account for the fact when your axis of rotation is different, okay? Because most of the time, I shouldn't say most of the time, but in the classical equation, the one that we have on the previous page, okay, the moment of inertia is computed assuming that the axis of rotation matches up with the center of mass. Okay. All right, so I'm going to do an example of a uniform rod. Okay. Because most of the times we can assume the limbs are basically the same as a uniform rod. Okay. And if we assume that the center of mass is at the center here, okay, okay, then the moment of inertia of this rod assuming that we rotate around the center of mass, okay? So let's say we assume that the center of mass stays fixed and the rod rotates around that, okay? Then the formula for this is gonna be 1/12 mass times the length of the rod squared. Okay? And so this length right here is L. Okay? Okay. And so depending on the different shapes, whether you have a square, whether you have a circle, then the formula for your moment of inertia is going to change based on those shapes. Okay. And remember, the reason we have different formulas for moment of inertia based on shapes is that different shapes distribute their mass, differently. Okay. Okay. All right. And so if we're rotating about our center of mass, that's a simple thing to do. And so we basically just look up in a table what our shape looks like, and then we just plug into that. Formula. Okay. If the axis of rotation is not at the mass center, then we have to compute a new moment of inertia based on the parallel axis theory. And so I'm gonna go ahead and draw that on the next page just because I need a little bit more. Okay. All right. Any questions on this so far? Okay. All right. And so let's say that we have our slender rod again. Okay. And then just like before, we have our center of mass right here. Okay. But let's say that now our rod is rotating around this pivot right here. Okay? Okay. And so the entire rod, is rotating around right there. Okay? And so let's call this point O. Okay? And so by the parallel axis theorem, the way that we compute this, this total moment of inertia around O is we take the moment of inertia around the center of mass, okay? Okay, and so it's not like we forget that. And so, we still use the I of the center of mass, okay? To this, we're gonna add the mass of our object, okay? Multiplied by the distance to the new axis of rotation squared, okay? And so the L that's here is this distance, okay? And so whatever distance that we moved away from the center of mass to the new axis of rotation, we have to multiply by that. Okay, so this IO right here is the new moment of inertia. Okay. And so, because, a lot of times when we consider human motion, the axis of rotation is almost never going to be the center of mass, right? And so if you consider, let's say that you just move your arm, right? Your arm is rotating around your elbow, right? And so if you consider the center of mass of your lower arm you know, it's not at the elbow, it's at the center of your lower arm, right? And so we have to use this theorem quite a bit in order to move our center of masses around, okay? And so we'll probably get to that, you know, on next Monday when we start doing some examples, okay? All right, and so last thing I wanted to cover before we leave for today is just a very quick review of polar coordinates. Okay. And so because we'll be doing angular motion here, it's actually really inconvenient to work in XY coordinate system. Okay? And so, you know, whenever you have any kind of angular motion, polar coordinates is actually the most convenient thing to work with. Okay? Okay. And so instead of XY, okay, and so we don't have XY anymore, what we're going to be working with is R and theta. Okay. Right. Where R is the radial direction, and so R is the direction that points from the center of rotation out to, you know, wherever object is, and theta is the tangential direction, and so that's going to be in the direction of the rotation. Okay. Right, so let me draw that on the next page, but before I do that, are there any questions on this? Okay. All right. And so if I draw a circle here, okay. And so we go, let's go back to our example of a rock traveling in a circular arc, okay? Here is our center of rotation, okay? We draw a line out, okay? Okay, and so this circle right here is center of rotation. Okay. And then out here we have the, you know, the mass, okay? So let's say that we have just an object at the end of a string, okay? And so this object is going to be rotating around this circle, and so it's going to be traveling along this path, okay? And so the R direction always points from the center out to wherever the object is, okay? And the theta direction is going to point tangent to the circle, okay? Okay. And so the terms that you'll hear me use for this is going to be the radial direction. And so the radial direction is going to be R. Okay. And then the theta direction, that's going to be the tangential direction. All right. And so this is going to be important because, you know, when we do our dynamic analysis, right? You know, our dynamic analysis, we're going to do the same as before. So we're going to sum up all the forces, okay? Okay. But instead of summing the forces in the X and Y direction, which is, you know, what we've done before, you know, in angular motion, we're going to do the sum of the forces in the radial direction, okay? And so the sum of the forces in the radial direction is going to be the mass times the radial acceleration, okay? Which we know, we have an expression for the radial acceleration, okay? And so this is going to be m times omega squared r, okay? I put a negative sign there because, you know, the radial acceleration always points inward, right? Okay, and so that's going to be in the opposite direction as the r, okay? This right here is radial acceleration. Right, and then the other component that we're going to do is we're going to sum up the forces in the tangential direction. Okay? And so there's going to be some of the forces in F theta. And so this is going to be equal to m A theta. A theta here is the tangential velocity, or tangential acceleration, excuse me. Okay. Okay. And the tangential acceleration is going to be r times alpha. Okay. Well, remember from the beginning of class today, this r times alpha is the tangential acceleration. Okay. All right. And so we're going to stop there for today because basically these two equations right here are going to form the basis of our rotational dynamic analysis. Okay. And so, you know, what we're going to do, and so next Monday, we're going to start off right with an example. We're going to do an example where we sum the forces just like we did before, but we're going to set them equal to these quantities instead of 0, right? And then from that, we'll be able to perform what's called an inverse dynamics analysis. And so, you know, we mentioned that a little bit last week. And so we'll actually be able to perform that on Monday. Okay. All right, any final questions before we wrap up for today? All right, question. So will homework 6 be assigned and due before Thanksgiving break? Or is it going to be held off until we get back on the break? So I plan on assigning it to you guys next week, but it's not going to be due until basically the very end of class. You know, I don't want to assign it before the midterm. And so it's going to be assigned early next week and then due, you know, it's going to be the last thing you turn in besides the final project. Yeah. Mm-hmm. All right, any final questions? All right, okay, so that's all we got time for. And so thank you everyone for tuning in. So remember, Wednesday is our midterm, so make sure everyone comes here for that, okay? And I'll send an email about that. And then the other thing I want you guys to think about is your final project topic. So make sure you're thinking about that and then select it by Sunday, okay? All right, so have a great evening, everyone. It's dark outside now, so, you know, if you're driving home right now, then, you know, drive carefully, you know, take care of yourself, okay? And I'll see you on Wednesday for a midterm. All right, Samson, you want to go look back at something, right? What was the part that you want to go back on? Oh, yeah, remote, this one, right? Yep, all right, see you. All right, so the whole idea with this equation here is that, you know, when you have an object that's rotating, you know, there's basically two components to it, right? And so you have the body itself that's rotating, but then we also have the overall kind of motion of the body that could be rotating around something else, okay? And so I think the easiest way for me to explain it is to kind of look at this, you know, leg right here, right? And so if we break down the motion of this leg, and I wish I can kind of, let me go to the end again. Okay. And so if we break down the motion of that leg, right? Okay. And so, you know, this line right here is representing our leg, okay? And so, you know, as the person completes the kicking motion, you know, the leg itself is going to rotate. And so it's going to go from a position where the foot is kind of like, you know, in the air, all the way to where the foot is on the ground. Okay. So let me kind of draw a foot here just to make it a bit easier. Okay. Right. And so by changing its orientation like this, we call this a local rotation. Okay. Okay. Right. And so that's the local rotation of the leg around its own center of mass, right? And so that's a change of rotation. But another thing that the leg's doing, right? And so if you go and kick, right? You know, it's not just your lower leg that's rotating, unless you're like One Punch Man, but for feet, right? And so it's not just that, but your entire leg is going to be going forward, right? And so your thigh is going to be put in motion, your entire core is going to be put in motion, okay? And so the leg, in addition to itself changing orientation, the leg itself is going through a large swinging motion just from the rest of the body, right? And so in addition to kind of rotating like this, right, where it's rotating around this center of axis, okay, the other thing that the leg is doing, and so if we kind of start from the kind of the initial position like this again, okay? You know, let's say that up here is the center of mass of the body. And so the other thing that the leg is doing is it's kind of rotating around this center of mass as well. So if you think of this, if you kind of think of this as kind of like a pendulum, right? And so if we kind of hook these two things right here, okay? The other thing that this leg is doing is basically going from here right? So we draw the center of mass again. And I'm going to exaggerate it just to make it a little bit easier to see, okay? But the other thing that it's doing is something like this, right? Where the entire leg is kind of rotated from a position like this to a position like that, right? And so it's the combination of the leg kind of changing its orientation and making this kind of big swinging motion around a different center of mass, that creates, the entire sense of angular momentum, right? And so this right here, this would like be remote rotation. Okay. And so angular momentum is a combination of these two things combined, okay? And most of the times it happens when you have, remote is kind of like it's like a bigger picture kind of thing. And so it's a rotation. Usually whenever you have a rotation around an axis that's not your center of mass, you're going to have both of these because it's a combination of these two motions. Yeah. Mm-hmm. All right. All right. Any other questions? Okay, great. All right. I'll see you on Wednesday then. You too. Or if you're home, then stay safe.